Okay, today we're going to look at the intersection of a line and a plane. So there are three possibilities when you do this, and I just want you to take a second to consider what those possibilities are. You've got a line and a plane. So you can imagine me standing in the front there with a piece of paper representing my plane and a pencil representing my line. What could happen? So the first one would, of course, be the situation where the line comes and cuts through the plane. So it would intersect and go through it. The intersection then would be a single point. If you think about it then, the direction vector of the line must be pretty different than the ones that are on the plane. They wouldn't be parallel, and so it would come and sort of intersect through the piece of paper and intersect at a point. The second one would be the case where you have the plane sitting on the desk and the pencil hovering over top of it. And the line would be parallel and distinct from the plane. So it's not only parallel, but it's also different from the plane. So it's separate, so hovering above it. In that case, there would be no intersection. You'd know that this would happen because the direction vector would be scalar multiple of one of the direction vectors on the plane, so it would be parallel, but point on it would be distinct to make it separate. And then the third, of course, would be where the line lies on the plane, so the pencil is right on the desk. So not only are the direction vectors parallel or scalar multiples of them, but that point is also on the plane. And if that was the case, you'd have an infinite intersections. And those classify your three possibilities. So let's look at an example. We're going to find the intersection of the line and the plane and the given plane. So, give you a second to write that down. We have a line and it's given with the equation L, and it's x minus 2 over 3 equals y minus 4 over 1 equals z plus 1 over 2. And then you've got a separate plane given with the symbol pi. Remember, this isn't 3.14, it's just a pi, Greek letter. And it's 2x minus y plus 4z minus 9 equals 0. So, three steps here. What we're going to do in all of these is assume that the line intersects with the plane. Because even if we compare the direction vectors, it's going to be difficult to compare it with the direction vectors that are on the plane because there's so many of them. You won't be able to tell really easily if it's parallel unless it just jumps out at you. So in this question, we're going to assume, in all the questions, we're just going to assume that they intersect. And then we'll go off and do the work, and what you'll see is something, if it intersects, then you'll actually get an answer, and if it doesn't, something weird will happen, and we'll be able to interpret what happened. So step one would be to put this line in parametric. So given the information in the line, I see that the point is 2, 4, -1. Remember the point coming from the top, opposite to what you see there. And the direction vector is the direction numbers on the bottom, which in this case is 3, 1, and 2, remembering that this is over 1, so we've got that. Have this two bits of information and we can write it in parametric form. So x equals 2 plus 3t, y equals 4 plus 1t, and z equals -1 plus 2t. Step two is then going to take this and assume it intersects the plane, which means we're going to take it and sub it right in here. So this is step two. So we take this here, sub it in, and so wherever we see an x, we're going to replace with the parametric version. So in this case, we'll replace x with 2 plus 3t. And then y, we're going to replace with 4 plus t. And z, we're going to replace with negative 1 plus 2t. And minus 9 equals 0. So by assuming that they intersect, there must be a value for x, y, and z that makes this statement true. We would find those x, y, and z that make up the point to make it true. Now it's just a matter of a little bit of algebra, so I'm going to rainbow 4 plus 6t minus 4 minus t. Rainbow of 4 is minus 4 plus 8t minus 9 equals 0. Collecting like terms, we get 13t on this side, and then minus 13 here equals 0. So 13t equals 13, and t equals 1. What it means that there was a value for t, a single value for t, that satisfied this equation. So finally, step 3 then. Plug this value for t into the line to get the actual coordinates. So we know that t is 1, so the x coordinate is going to be 2 plus 3 times 1 is 5. The y coordinate is going to be 4 plus 1, also 5. The z coordinate is negative 1 plus 2 times 1. Oops. Negative 1 plus 2, which is 1. And so therefore, the point of intersection is 5, 5, 1. So recapping the steps, we take the line, put it in parametric so I have a value for x, y, and z, sub it into the plane. Wherever you see an x, replace the x component, the y, the z, solve for t. In this case, because there is an answer, there is a single value for t that works, we found that value for t, plug it back into the line to figure out the actual coordinates of 5, 5, and 1.